support vector machine regression, we are going to start by importing NumPy, Matplotlib, and sklearn. And then we are also need to import the SVM library. So from sklearn, import SVM, and that's going to import support vector machines. Now I want to go ahead and we need to build our data set. We're going to go np.random, random.seed. I'm going to seed it with 2, which is my favorite number to seed stuff with, which is, but it gives a pretty good data set. M is equal to 100. X is equal to 6 times np.random m comma 1 minus 3, just to move the x down a little bit. Y is equal to 0.5 times x squared plus x plus 2 plus np.rand random.rand n and m comma 1. This is just adding a little bit of noise to my data. Then y is equal to y.ravel, R-A-V-E-L, and that's just going to get the y into the same format. Okay, so 6 times np.random, boop, definitely not that, .rand, R-A-N-D, without the n, we're just going to go Gaussian, R-A-N-D. And then here you go, np.random. There we go. Now I should have my data. Now let's go ahead and plot the data. So plt.figure, plt.grid true, plt.plot x comma y comma plt.x label, and then let's go plt.y label. Hit F5. Let it be EL. Hit F5. All right. There's some data, lots and lots of data, a little bit more than the plots that we were talking over, but that's okay. Do that on purpose. Now let's go ahead and train an SVM regression for this. Again, remembering that only the data outside of the curves is what matters. The data inside the curves don't matter. So SVM regression, first I need to create a model. We're going to go SVM underscore regression, reg equals sk.svm.svr. Now we're going to go kernel is equal to poly. Again, that's going to be the kernel that allows us to do non-linear support vector machine regression. Degree equals 3. I'm going to go C equals 1, just so we have a very unconstrained model, and it's going to be able to do pretty much anything it wants. Epsilon 0.8, that's going to set the width of my street, and gamma is equal to scale, which should be the default, so it shouldn't matter, but let's go ahead and put it in. Into our call. And now I'm going to go SVM underscore regression is dot fit, and again I'm going to fit it with my data X and my target's Y. It's a capital X and a lowercase y. Let's hit F5. Everything runs, so it looks like our model is training just fine. Now I need to do a little bit of processing here for plotting purposes. So we're going to go x1 is equal to np.lin space. That's got to be from -3 to 3 to 100. Dot reshape from 100 to something that's 101 long. And then y underscore prediction, so PRED, that's going to equal to what my support vector machine is predicting. So we're going to go SVM underscore regression, which is our trained model. And we want to predict for all of our data x1. And now I should be able to run that and I get no errors. So I've created my model and my prediction. If I come over to my variable, I should have this float of this is what it's predicting. And you can kind of see just from the colors that you're getting at least a movement of shape. So let's go ahead and plot the SVR model on top of the existing data. So to do that, we need to go plt.plot x1 comma y underscore prediction comma give it a dash comma line width equal to 2. Just make it a nice thick line. We're going to go label. Let's do a fancy label. So we're going to put it in $ so we can put it into LaTeX. And we're going to go dash hat. That gives it the little triangle hat for Y. That's going to be Y hat. PRED will be needed for your prediction. WIDTH. Need to get it better. Okay. And there is our model, which doesn't quite look like what we want. But if we think back to the degrees that we put this in, it doesn't really make sense to have a third degree there. So maybe let's try 2 degrees. That gets us a much closer model, but we can play around with parameters as needed. We're also not regularizing it very well. But before we mess around with that too much, or the epsilon or the street, let's keep plotting our data. So I'm going to go ahead and copy this line down because I want the same data, but now I want my Y prediction to be my street. So I'm going to go plus SVM underscore regression dot epsilon. And that should give me my epsilon positive. Now I want to make this a green line that's dashed. I don't want it as thick. And I want my label to read curb. And now I get this green line here that's a curb. And then what I can do is I can copy that down and Control C, Control V, and I can change my plus to a minus. And now I should have my top and my bottom curb. So I've now got a model that kind of cuts through it. Maybe we can change it to red so the curbs show up a bit more clearly. There we go. And now I've got some curbs that should be able to fit it. And now I'm a little bit interested to make sure which one of these models are actually fitting as my support vectors, or which one of these data points are showing up as my support vectors. So I should be able to pull that out of my data. So we're going to go plt.scatter. It's going to open up a scatter plot. I'm going to go capital X. Now I want all of my X that is SVM underscore regression dot support underscore. What this function here should give me is a lot of Booleans, or sorry, a list of all of my support data points. So these are all of my supports. So it's going to plot all of those for X. Now I want to do that exact same thing for Y. So we're going to go lowercase y and same as before, SVM underscore reg dot support underscore. That should go ahead and plot it, but we're going to go S equals 100, which should give me a very large marker. And we're going to go marker is equal to an O. That should give me a circle. I'm going to go face color is equal to none. And edge colors is equal to gray. So face color is equal to none. Get rid of that real quick.
You have marker minus O.
Thank you. Not, there we go. Perfect. So now I've got all of these markers, and if you zoom in, you can see that my data on the outside is a support vector, and my data on the inside is not going to be adjusting it, right? So now that I have this, I guess the last thing we might want to add is plt.legend. We're not too worried about where the legend falls. We'll just let it float to where it wants to be. And now all we have to do is tune our hyperparameters to get something that actually looks closer here. So maybe we can increase C to 1,000. That looks slightly better. I can increase epsilon to 1.5. That gives me a wider street, but doesn't really fit better. Maybe C at 100,000. Definitely taking longer because it's probably processing more data. Figure 1 is not responding. Force quit. Well, that's still not great. What if we try a third degree polynomial? I don't think it's going to help, but well, it did not like that. So let's bring that down to 10,000. And back to degree 2. Let's give it a wider epsilon and see if we can get something to fit. Oh, there's a wider epsilon. See if we can get it to fit with the radial bias function real quick. That fit, there we go. That fit very quickly, but doesn't look awful. The degrees are a bit high, but maybe we can bring down bring down my regularization. Starting to look a bit better. There you go. That doesn't look too bad, right? Starting to curve off at the side, which isn't really what I would expect it to do. We could bring down my street value to 1.5. There we go. That looks pretty good.
You actually changed the kernel.
What?
You changed the kernel.
Yes.
RBF only.
I changed the kernel to RBF, correct. So there's no right or wrong answer to what the kernel should be, right? It depends on your data.